So our group did a retaining cantilever wall, and things to know about the retaining cantilever wall is it's one of the 4 different retaining walls in the world. There's a gravity, a piling, an anchored, and then of course there's the cantilever wall. The cantilever wall is the shape of a T. As you can see, we have a nice 3D printed version of our cantilever wall, thanks to Ethan. It's 10 feet, the base is 10 feet, and the base is 3 feet in height, and it's 10 feet in length. The wall itself is actually 12 feet in height, and the base is 3 feet in height as well. Other things to know about the cantilever wall: it's made with concrete, and it's with steel bars that are poured onto the steel bars running through the concrete that was added. And the retaining cantilever wall is commonly seen in front of houses that are at a high level, and that's used to use like as a bridge for the lower level land. And it's one of the most commonly used earth retaining walls. And for this project, our objectives that we're going to show is the dimensions, like I showed the dimensions of this wall, the materials, the economics, the static calculations, and the problems that we have faced.
For this project, we'll be doing the retaining cantilever wall in someplace sandy. We'll be going to the Arizona desert. Why Arizona? Because there is no snow and no rain, so there'll be no surcharge forces on the wall. Now, for the economics, there'll be no labor costs and no time costs. And here for soil, we'll be using sand, and there will be no steel inside the rebars in the wall.
Some things to know about the cantilever wall: it's made of a stem and base slab, and the stem and base slab is made from either 3 types of different concrete. That could be a reinforced concrete, it could be a precast or pre-stressed concrete. And an easy thing about the an easy and convenient thing about the cantilever wall: it can be transferred from place to place. It can be made at say like a construction site. It can be made at any place, and it can be easily transferred from like a factory to a construction site. So when we say that it can drop down from a higher level seamlessly, the right side of the wall, it's kind of all of this, you would say, is about, this is all soil pushing up against the right, and this wall is really just pushing up. And you could just picture a house right here, and that's where the wall is holding the entire, it's like not holding, but it's pushing against, so the level will stay up high. And right here, although to the left of the wall, remember that the wall is underground, to the left of the wall, it would just be like anything down, anything that's maybe sea level, or it could just be like a road or anything like that.
Due to the terrain of the Arizona desert, we use certain materials for this project. As material, we use poured concrete, and we use the sand as our soil. And the unit weight for the sand was 99.88 psf, and unit weight of the poured concrete was 145 psf. The problems that we faced during this project would be changing labor costs, because in real life the costs frequently changed and we couldn't really get a good read on what the accurate amount was. For the second one, we calculated the steel rebar inside of the concrete was a big problem for us because of the density, and almost everything around it would like change, so we couldn't really get a good read on that, so that's why we took it out completely. For the other one, we didn't have really accurate pricing on any of the materials. Everything that we looked up had a different pricing for everything we had, due to the concrete all the way to the sand. So either way, we couldn't really get anything accurate going on. And then lastly, for everything we had, the statistics, we had different equations to go with it. So we usually just picked the best ones we could find and just went with it, not knowing that it was right or wrong.
While designing our cantilever retaining wall, we do have to take into consideration some issues that may occur. These issues include sliding, sinking, and even overturning. These issues may happen or occur due to natural earth pressures, active earth pressures, or even the soil itself. With these issues in mind, we made sure to tackle them in our calculations. So, our calculations include the lateral soil pressure, the soil pressure on the back of the wall itself, and even the overturn moment. With these calculations, we were able to make sure that our wall was strong enough and sturdy enough to maintain the different pressures applied to it.
So for this part of the video, we're going to go over the calculations of the statics of the entire cantilever wall. So first off, what I did was did the lateral soil pressure of the back of the wall. So it's the pressure pointing that way into the back of the wall from the soil itself. So we had two equations we needed to use. The first one being P max equals Ka of the unit pressure, unit weight of the soil times the height of the total wall. So before we could do that, we needed to find Ka, which is just tan squared 45 degrees minus 5 over 2. So just plugging that in, we came up with tan squared 45 degrees minus 30, which is the angle of the sand on the wall, divided by 2, which came out to 0.33. So from there, we took that number, plugged it back into the equation. So we got 0.33 times 99.88, which is the unit pressure or unit weight of the wall, times the height of 12 plus 3, which comes out to 15, and that gave us 494.4456 pounds per square foot. So after we did that, we were able to move on to the soil pressure on the back of the wall from the sloping backfill, which is this here with that angle. So what's happening is the soil's pressing down on the wall from an angle of 26 degrees from this line. So just like the other one, we had two equations, which was the P max, Ka, times the unit weight of the soil times H. And then to get Ka, again, we had to use a different equation, which is cosine B, B being the backfill angle, which is 26, cosine B minus the square root of cosine squared B minus cosine squared 5, over the same thing, but instead we're adding it. So we just went along and plugged it in, 26 being backfill, and 30 being the same phi as we used in the last equation, and that all came out to 0.7206. So we took that number and plugged it in to the P max equation and got 1,079.6 pounds per square foot. So continuing the calculations, the next part we're going to head into is calculating the lateral soil pressure and overturning moment. So overturning is just it flipping over in either direction. So we're calculating about this point here, F of H, and then F of H pushing the wall. So just like the last equations, it's P max, Ka of the soil, unit weight times the height. So we just copied this straight over from the last calculation, which is the same number. And then the new equation we end up having is F of H times 1/2 P max of H. So the 1/2 is 1/2. We take the P max that we calculated earlier, plug it in, and then the height of the wall, which is 15 total, 3 here, 12 here. And that gives us 3,708.045 pounds per square foot. And that is our sliding resistance force, which equals HF. So now we're going to go into the overturning moment, which is MTO, which equals our sliding force times 5, which is our halfway point of our wall, which the length is 10 feet in total. So that came out to 18,540.225 pounds per square feet. So that goes over the overturning motion. So coming to the next part, we have to calculate the weights, the resisting moment, and the sliding force. So first we're going to go weight of the soil, which is the area, which is 5 times 12 height, times 145, which is the unit weight of poured concrete, and that comes out to 3,480. And for the soil, we do it, but with the sand unit weight, and that'll come out to 5,992.8. And then for the footing, which is the bottom part of the wall, is the 3 feet thickness and the 10 feet length times the unit weight of the concrete, which is 145, and that comes out to this. So the total weight that the wall can take is here, after adding it, is 13,822.8 pounds per foot. So after we have that, we can go down to the resisting moment, which is MR, about the toe. And the toe is this section right here. So that is overturn or slide. So what we did was take each of the unit weights, and we multiply them by a certain distance. So we split it into 3 different distances: 7.5, which is 3/4 point; 5, which is the halfway point; and then 4, which is the other quarter point where most of the pressure is going to be. And after like adding and calculating that, we end up with 80,616 pounds per square foot. So from there, we can take this number and calculate the sliding resistance force, which is just Fr equals mu times the W total. What mu is just the friction between the wall and the sand on the bottom of it rubbing. So that just came out to 0.5 after some research. And we multiply it by the 13,000 number to get 6,911.4 pounds that it can reverse sliding. So finally, what we wanted to figure out after everything is the factor of safety. So the first factor of safety is overturning, which is just MR and OT, which we calculated earlier. So we just divide the two and we ended up with 4.35, which is larger than the minimum 1.5. So we know that our calculation there is good. And the last factor of safety is the sliding. So that just equals FR over FH, which is these numbers here. And we had got 1.86, which is above the 1.5 minimum. So we're all good there.
Okay, so for the engineering economics and economic decision making for the cantilever wall, what we did is we were just going to find the cost for the concrete, but we'll get to that soon. So for the cost of the concrete, first we had to take some steps into account first, and first we had to find the volume of the entire wall. So for the volume, we first found the volume of the base, and the base, of course, is 3 times, we did length times width times height for volume, and it's 3 feet in height, 10 feet in length, and 10 feet in width. So that equals 300 cubic feet. For the volume of the wall, it's 12 feet in height, 2 feet in length, and 10 feet in width. So that equals 240 cubic feet. The total volume is 540 cubic feet. And converting that into square feet, that is 66.32 square feet. If the cost of the poured concrete, the reason we put it into square feet is because we found that it's $20 to $25 per square feet. So we just chose $25 for every square foot of poured concrete. So simply all we had to do is do 66.32 square feet of concrete times $25 per square foot of concrete, and that equals 1,658 per square foot of concrete. And other materials we used was the sand, of course, but the sand we're not gonna do any economic cost because we got it for free. Just want to simply, we would go to a beach or we would go to a desert and just get sand. And the reason we also exiled the steel beams, and for that reason is because it was not cost efficient.